Welcome, people who are watching this in the future. You missed 2 slides, but that's my fault, so I'm sorry. Okay, welcome back. The question at hand is, does a time shift change the energy of a signal?
No.
No. If I move a signal left-right on the time axis, I haven't changed the area under its square, and so my claim is that this is also the energy in x, because energy is time shift invariant. Okay, and then I guess also you could just see that because I wrote it down here on the third line. This integral is exactly what we saw on the autocorrelation slide, provided x was real. If x is a real value, then x conjugate is equal to x. Okay, so far so good. I guess, is it so far so good for you? Are you following? Okay. So what we have here at the end of this slide is, believe it or not, I think it's a polynomial in epsilon. Right, this is a second order polynomial, which means if we were to plot this for varying epsilon, we would have a parabola. Right, so we fixed x, and if you fix a t value, which we're doing here, if you consider this for multiple epsilons, this has to be a parabola. And this inequality is exactly what we established up here. And so what this line is saying is that we have a parabola that is always non-negative. So we could have an instance that looks like this, or we could have an instance that looks like this. And how do I know it's an up opening parabola?
Doesn't go below 0.
Oh, yeah, that's a great way to see it. Yeah, if it were down opening, it would have to cross 0. Additionally, energy can't be negative, and so if I have a positive coefficient on the squared term, that also means I have an up opening parabola. But good, keep me on my toes. Good work, people. So the reason that I note the kind of the possible vertex locations of these parabolas is that if I know that the vertex is never negative, then I know something about the discriminant of this parabola. Said another way, the roots of this parabola are either repeated or they're complex. Yeah, because we can't have this situation, which would give us 2 real roots that are distinct, we are restricted to only have either repeated roots or complex roots. And the way to say that in math speak is that your discriminant has to be non-positive. What the hell's a discriminant? Well, it's the thing under the radical when you do your quadratic equation. So that means that b squared, so 2 times rxx of t squared minus 4 times a times c is non-positive. Right, so where did I get these a, b's, and c's from? I'm using the quadratic formula, where this is little a, this and this together are little b, and this is little c. And that is supposed to be a 0. Okay. So what else can we say here? What have we got here? We've got 4 rxx squared of t is less than or equal to, I think this means that rxx at any value of time If you square that, it has to be less than or equal to e of x squared. And Wiener-Khinchin tells us that the energy in x is the autocorrelation at 0. So I think if you pick the left-hand side of this line and then use the inequality with the right-hand side of this line, we have just shown this implies that Rxx at any t is no bigger than Rxx at 0, which is an equivalent statement to saying that the function is maximized at t equals 0. Let me take a side note here and say that this is not the only way to prove this. I think it's kind of neat because we get to use high school topics like parabolas opening upwards and downwards to prove something in your 4th year of electrical engineering. I just like that. Questions on this proof? This isn't supposed to be ground shaking, again, because you can go ahead and think of this as the signal is never more similar to itself than when it's unshifted. Okay, so why the hell would anyone want to do correlation, either auto or cross? So I think that the best application that I can sell you on right now is this idea of using radar to determine how far away an object is. Okay, so radar ranging is what we call it. And so the picture is, I've got a radar antenna and I'm gonna send out an RF pulse, and I'm gonna call that x of t. And the literature says that x should be real and impulsive, which does not mean like has no self-control. It means looks kind of like an impulse, like short and tall, that kind of deal. Sorry, short and tall. Short duration, large amplitude. There we go. How many of you just written your notes short and tall? Okay, so if that pulse goes out, it will nominally, if there's nothing else in the universe, it will bounce off the first object it sees and it will return back, or some version of it will return back. We have to account for attenuation. So alpha is this attenuation. Right? If I have an RF signal and I beam it out and it comes back, it has traveled quite far. And so the power in the signal has to diminish with your R squared law. So the received signal back will be smaller. We'll call that the attenuation factor. It will also be delayed, right? So the signal that I get back, if it is a reflection off of some object, it has to take some finite amount of time to get there and some finite amount of time to get back. And so if we wanted to estimate this distance, this range, I don't want to use the letter R because we're talking about autocorrelation. So let's talk about this distance D. If I wanted to estimate D, I could do that in one of two ways. I could use the attenuation that I see in my received signal Y, or I could use the delay in my received signal Y. And so what we're doing in this application is we're going to try and capitalize, we're trying to measure that delay, which is in general an easier thing to measure than the attenuation. Okay, so do you buy the claim that the received signal is going to be a delayed copy of the sent signal, where I don't know T naught, or T naught depends on the distance, alpha depends on the distance, and the received signal is also going to be corrupted. And the corruption I'm going to call N of T for the noise that we get. So if you buy that, and there are other assumptions that I guess I haven't stated, that mainly there is an object out there, it's not moving, or else we have Doppler to contend with. There are no other objects that we could get reflections off of. So I don't know. I guess if you start talking about all the assumptions, this does not become a very practical problem. But if the beam is collimated, if it's very directional, and the object is moving slowly relative to the beam speed, then all of those things that I assumed, they actually start to make sense. Okay. Okay, so let's take the received signal, y of t, and we're going to put it through some processes. This is so it's supposed to transmission antenna, and then it waits some time to be a receive antenna. And so those processes is just an LTI system whose impulse response is matched to the impulse that we sent. Okay, so if you're looking for vocab here, this is called a matched filter. Matched to what? Matched to X. It's not a filter whose impulse response is X, it's a filter whose impulse response is the time reverse version of X. And if you're wondering how we do that, hold on, we'll talk about that at the end. All right, so if you're imagining this in the time domain, then X is some spike that has finite duration, hopefully, and it has a lot of energy. So if we call the output of this matched filter Z, then we know that our LTI theory tells us that the output is the impulse response convolved with the input. So here's the impulse response. Here's the input. But we can expand our input as the sum of two terms. It's the alpha, I think that alpha should have been there. No, sorry. There's a typo here. It's not an important typo, but we should call attention to it. This alpha ought to live inside this bracket. Yeah, because the alpha only appears multiplying X here. It does not appear here. Okay, sorry about that. Okay, so we're convolving a time reverse version of X with the sum alpha X of t with some delay plus the noise process. Well, okay, we can just brute force this convolution if you like, and we can, right, because convolution distributes. So the convolution of a function with a sum of functions is the sum of convolved functions. And so that's what I'm doing here. I'm using distributivity. There's no way I'm going to write that whole thing. Distributivity of convolution. And so what are we looking at here? I believe that this has the flavor of an autocorrelation, does it not? All right, it's the infinite integral of X with itself. So, but there's extra junk in there, isn't there? I think this is Rxx if we were to evaluate it at t minus t naught. Yeah, I think that's how that works. Right, because if Rxx of t is the integral of x of a dummy times x of the dummy minus t, then if I time delay this, Rxx of t minus t naught, well, then everywhere that I see a t up here, I replace it with a t minus t naught. So integral of x of tau times x of tau minus t plus t naught. d tau. And so at first blush, what I just wrote and what I have over here on the right-hand side of the slide doesn't look like it's the same thing, but I think if you did a variable sub, you could get it to, you could force it to the right form. In particular, if I let tau minus t naught be lambda, then I think I could get this integral to look like that integral. Okay, so these are equivalent up to a variable sub. Okay, so the first term looks like a scaled version of Rx of the autocorrelation with a time delay itself. And then over here, we've got what looks like a cross correlation. Okay, so then this signal z, if we were to plot it, versus time, it would look like a scaled version of the autocorrelation of x, whose shape we don't actually know that well. Once we well define x, then we could know what its autocorrelation would look like. But it's going to be corrupted by this signal over here. Now let's talk a little bit about this cross correlation. This represents how similar x is to the noise process. Now, do you think that that similarity, whatever it happens to be, changes if I shift x left or right? Especially if the noise itself is white, if the noise doesn't have any correlation between now and now, then how the hell is its similarity to a fixed signal going to differ if I slide that fixed signal over it? And so that's my argument for why this is going to be roughly constant. And again, that argument goes, this is a measure of how similar n is to a shifted version of x. Shifted by how much? T. So pick your favorite value of t. If I change that t, I don't think the similarity between n and x should change very much, provided that the x we picked doesn't look like noise. Okay, so if we pick something impulsive and not fuzzy and noisy, then this will be both a small number and a constant number. Okay, so maybe it's not going to be exactly constant, so it'll be, I don't know, some kind of baseline that we have to contend with. That's going to be this term. But what do we know about Rxx? Well, from the previous slide, we know that it's maximized when its argument is 0. And so on top of that kind of noise floor, we're going to have some function that achieves a maximum at some point in time. And what time is that?
T naught.
T naught. Good. So if you take the received signal on your antenna and you pass it through a matched filter, and then you look at that signal on the oscilloscope, it's going to have some fluctuating value. It's going to reach a peak, and it's going to go back down again. And you, as the radar operator, can say, oh, I know when we sent the pulse, and I know when the peak occurred. Therefore, I now have an estimate of T naught. And the whole idea is we need to estimate T naught because we can then use the speed of light to determine the distance to the object. So the range is then going to be 1/2 the speed of light times the time it took to go there and back again. Questions on that? So clearly it's not going to be a human looking at an oscilloscope screen. It's going to be a circuit or a computer that has to decide when has the peak been reached, but you have seen peak detection type circuits before, or that concept isn't particularly novel, right? We can build circuits or computers that can do their best guess at when a peak occurs in a signal. There is a chat that I have been ignoring. The question is, would that work the same if we used a sinusoid as the signal that was sent? Yes, but you have to make sure that the pulse you're sending is of finite duration. So what I drew here was this kind of positive pulse. In fact, what it would usually be is a amplitude modulated sinusoid. So in fact, this is likely what's going to be coming off of the antenna. So the pulse would be kind of a baseband signal, but if you modulate that up to the passband, then all of a sudden it can fit on this antenna that you have sitting around. Okay. And nothing about the derivation needed to know what the pulse looked like itself. Now, if you modulate it up, then all of a sudden this operation, or building a circuit whose impulse response was that pulse, becomes a little harder, because now you have to worry about synchronizing your oscillator here with your oscillator here. But it's not as hard as you might think, because guess what? They're co-located. They're sitting at the bottom of your antenna. And so this is not your classic communications problem where you have to match an LO over here with an LO like physically distance. You could use literally the same oscillator to generate the transmitted pulse as you do for the received pulse. Or sorry, the matched filter pulse. Jack, did I answer your question? Cool. Is anyone concerned that I have specified an impulse response to be a time reversed signal, especially because I drew that signal in forward time as being causal? Does that give anyone kind of the heebie-jeebies? Right, what happens if I time reverse X? I get a signal that's not causal. And if I have an impulse response that's not causal, I have a non-realizable system. So in practical terms, I didn't include this in the derivation because it tends to muddy the waters a bit, but in practical terms, you can actually get the same behavior, right? You get this peak behavior if you replace the true matched filter with a causalified matched filter, big T minus T, where big T is the pulse duration. Because now all of a sudden, if I shift this by big T, I still get something that looks like it's reversed in time, but now it becomes causal. So this is now lasting from 0 to big T. And this is my new impulse response. Like I said, the math works out the same. You end up getting this autocorrelation that's shifted in time, but now it's shifted in time twice. Once by the inherent delay that we had to introduce, and once by the delay introduced by the traveling of the beam out and back. So I think I'll include a homework question that asks you to go into this detail a little bit further. The moral of the story, you can't get anything for free here. That is, if you want a buildable system, you have to pay for it somehow. And the price you pay is actually related to how close does your system work, right? So this should work for any positive T naught, including if the if the device, if the airplane is sitting right in front of your antenna. Right, there's no limit on T0 in the original picture. There will be a limit on T0 in the practical filter. Okay, so I think we'll include that in a homework question. Cool, time is 10 till. All right, we got this. All right, this is a really nifty result, and its implications are further reaching than you might expect at first. It's certainly further reaching than I first gave it credit for. I'm still kind of appreciating the depth of this result. So what am I saying here? The claim is that the autocorrelation of a function, once you Fourier transform that, you get the energy spectral density of that function. So this is the Fourier transform symbol. I think we should pause here to recognize that is crazy talk. Like the autocorrelation, which has to do with shifting and measure of similarity, is if you take that function, which is itself a function of a function, if you take that and you map it to the Fourier domain, you actually end up with the energy spectral density of the original function. So quick review, what is energy spectral density? It is this function. So x of f, the Fourier transform of x squared. It's the idea that if you integrate this function over some band, you get the energy in that band, hence energy density. Okay, so let's go ahead and prove that. On the first line here, we have the Fourier transform integral. So this is, you take the function you're trying to transform and you multiply by a complex exponential and you integrate over all time. Okay, and then in the second line, I have replaced the autocorrelation, which is itself an integral. So this is supposed to stand for that. And if you're paying attention, you realize that I dropped a d lambda here. Okay, so another typo. There ought to be a d lambda from the autocorrelation integral. Right, because the d tau was already there. I threw another integral. There has to be another d something. So d lambda is what's missing. All right, so in the next step, we do something that makes mathematicians cringe, and we exchange the order of integration. But your safety word is that if both integrals converge, then you can go ahead and swap their order with impunity. And so I guess we're assuming that both of these integrals exist, and that the autocorrelation exists, and that the Fourier transform exists. And if those are both true assumptions, then we can do this swapping of integrals. So before we were integrating lambda on the inside and tau on the outside, and now we've swapped that. Now it's tau on the inside, lambda on the outside. Okay, so what's going on now? Well, on the inner integral here, this integral over taus, yeah, what are we looking at? This is the Fourier transform of x-ish, yeah? It's not quite the Fourier transform of x because there's this shift in here. I guess I just gave away the ghost. It's a Fourier transform of a shifted version of x. So we can use the Fourier transform shift property and say this is the Fourier transform of x, but shifted in the time domain. Shifted by how much? Shifted by lambda. And so we get e to the j 2 pi times f times lambda, which is that that time domain shift property that we covered on Monday. Okay, we're not done integrating, but luckily, part of what we just got is independent of lambda, and so it actually pops out. And then what are we left with? I think now it's worthwhile to write this out. We got big X of f on the outside, integral over all lambdas of x of lambda e to the positive j 2 pi f lambda. D lambda. Which is also almost a Fourier transform. The only thing that's missing is this negative sign in the exponential. So we could fix that if we say this is the Fourier transform evaluated at negative f. Right, because if I replace f with negative f, then all of a sudden I get that negative in the exponential and I get the true Fourier transform integral. All right, the last step in this proof is actually contingent on something I haven't mentioned, is that we're talking about a real valued signal x of t. And the last thing I'm asking you to remember from 228 is that if I have a real valued signal, then its Fourier transform is conjugate symmetric. That is, if I reverse it in frequency, I take its complex conjugate. So in my 228 classes, I called this Hermitian symmetry. You'll also see it called conjugate symmetry. All right, so after a couple of observations and substitutions, at the end of the day, we get the Fourier transform of the autocorrelation is a product of the Fourier transform of x with a conjugate of that function. And if I multiply a number with its complex conjugate, that's the same as looking at its magnitude squared. Which is how we defined the energy spectral density. There is an analogous result for power signals, right? It only makes sense to talk about the energy spectral density of energy signals. If you have a power signal, then you have to talk about the power spectral density. If you replace the definition of autocorrelation with the autocorrelation for power signals, then actually the exact same proof works, and you get this relationship that the power spectral density, which has this symbol S sub x, is equal to the Fourier transform of the autocorrelation of the power signal x. I realize that this is a little confusing, but if you have an energy signal, you want energy spectral density. If you have a power signal, you want power spectral density. And if you need help remembering what an energy signal, like what in your mind an energy signal should be, think finite duration. So like a finite duration pulse has a fixed energy, so it's an energy signal. A periodic waveform is not an energy signal because it has an infinite amount of energy, but rather has a finite amount of power. That is how I presented it in 228, energy versus power signals. But in this class, we are going to extend the notion of power signals from just periodic things to random things. So get ready for this on Friday. We're going to start talking about the spectrum of random signals. And the appropriate spectrum to talk about for random signals is typically the power spectrum. And we'll talk about why that is on Friday. But I'll close this up with an appeal for questions if you have them. Okay, I will, again, I apologize to the people watching this in the future who missed the first 10 minutes of lecture. I'll try to record better next time. Thank you. I'll see you Friday.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.